All right, good morning, everyone. Just before we get started, those of you who are familiar with how this GoToWebinar works, I just want to do a little quick sound test. The questions platform would be the best place just to see if everyone can hear me. So if one or two people could just type right in there and let us know if you can hear us, that would be great. Great. All right. So I am seeing some people saying yes. So let's jump right into this. So good morning, everyone, and thank you for joining us for another episode of our 20-minute webinar series. This episode is called Boiler Efficiency 101, what most manufacturers don't want you to know. It's a common misunderstanding that the sole determining factor for boiler and water heater efficiency is the water temperature entering the unit, and that having a high turndown will guarantee efficiencies north of 95%. In this presentation, we'll uncover some truths for you and get you pointed in the right direction. As a reminder, this series will only be about 20 minutes of presentation. The idea here is to give you a high-level overview of some problems and solutions and get you thinking. It's a quick crash course, but we find that the Q&A at the end gives you the opportunity to get more involved and understand the things that you wanted to learn. After the 20 minutes, Rath Associates wants to do our part to help the first responders and charities who are doing a lot during these uncertain times. We've already given away $3,000 and are looking forward to continuing that mission. We'll send out a quick poll to get your input on which charity you'd like us to donate the $500 to this week. After that, we'll get right back to the Q&A. Today, we have the pleasure of having Dr. Lou Vorseveld from Lars Heating Systems to give the presentation. Dr. Lou has 25 years of experience in the North American market in the boiler and volume water industry, at a variety of engineering, general management, and sales positions working for both the European and North American-based boiler manufacturers, covering residential and commercial boilers and water heaters, both condensing and non-condensing. He's earned his BS, MS, and PhD from the University of Vermont with a concentration in thermal sciences and combustion. So basically, he pretty much knows his stuff. For those of you that are new to the GoToWebinar platform, this is what your screen will look like. The two most important buttons are the question button and the handouts button. And I think a handful of you have already seen that question button, and thank you for jumping in and just letting me know that you could hear me. What I'd like for everyone to do, please, everyone, if you could just type in a question right now. I'd like to see what you're all looking to learn from this presentation. And if we see any comment threads or anything that's particularly interesting, we'll try and address it at the end. So please go ahead and just do that right now. Just plug that in. Within the handouts, you'll find these PDFs available to you. We've got a copy of the presentation in the PDF form, as well as a couple of the Lars boiler and water heater brochures. To find more, you can visit our website, Lars' website, or reach out to us at support@rathassociates.com. To view this presentation again, or to check out some of our other webinars and videos, you can visit our YouTube channel. We have our 20-minute webinar series on there, as well as a couple of PDH courses we presented and more. If anyone has any questions they'd like answered, or if you have any project that you need assistance in designing or equipment selection, our commercial development team is here to help. So without further ado, I'm going to open this up to Dr. Lou. Dr. Lou, why don't you take it, go ahead.
Yes, good morning, everyone. Thank you very much, Greg, for the introduction. I want to talk about Boiler Efficiency 101, some of the hidden secrets that boiler manufacturers don't want you to know. Here's just a quick overview here. I want to talk, first of all, talk a little bit about some of the common knowledge components that we know, that we're familiar with regarding efficiency, understanding the role of latent heat, the all-important item of return water temperature, as Greg already mentioned. And we also want to talk a little bit about what are the effects of turndown, high turndown, and how do we really harvest all the benefits of all these technical features. Then I want to go a little bit deeper into the combustion process, because as we go into the combustion process, we get the variables of combustion. We want CO2, low CO, low NOx levels. What are some of the driving factors to achieve those? And the item that will come up over and over again is called the concept called excess air. CO2 and O2 levels, and what is really the effect of excess air in terms of reducing emission levels. Most recently in the commercial boiler space, we've definitely seen a trend towards a number of manufacturers introducing O2 trim packages as standard or as an option on their commercial equipment. And what are the benefits of O2 trim? We'll talk a little bit about some of the different O2 trim systems available, and really, and it's really the crux of the matter, how we can drive and ensure optimum efficiency by having an optimum dew point and excess air control. In terms of, condensing boilers have been on the market now for probably about close to 20 years, and it's all about recovery of latent heat. As we burn a fossil fuel, natural gas, propane, oil, whatever it might be, basically we get CO2, we get water vapor, and non-condensing appliances, that water vapor goes up the chimney. What we want to do in a condensing appliance, we want to recapture as much as possible of that water vapor, get that water vapor condensed down to a liquid, and then the energy that we regain go back into the boiler water and increase the efficiency. What we're really talking about here is really dehumidifying. One way of looking at it is really dehumidifying the exhaust products and reclaim the heat, have that water vapor instead of going up the chimney, have it go down the condensate drain. Let's see here. One moment here. In terms of overall efficiency increases due to flue gas condensation, we have a couple of three different factors that combine here. First of all, as we reclaim that water vapor, actually there's about 1,000 pounds of energy, 1,000 pounds of BTUs in every pound of condensate. And if we have under ideal conditions, a 1,000,000 BTU boiler, it will produce about 10 gallons of condensate per hour when we run that boiler at ideal conditions, low temperature, and we'll talk more about these ideal conditions. Also, lower flue gas losses also are much lower because sensible as well as the latent heat energy has been almost completely transferred to the boiler water temperature. Hence, boilers are running up to 85 and north of 89 or 95% efficiency. Because of all these lower flue gas losses, all the heat that's not going up the chimney, we now have lower standby losses due to low boiler water conditions, and also much lower stack temperatures and drastically reduced stack losses. There's a lot of factors that go into condensing boilers. Here's just an overall summary. I want to focus a little bit here on, first of all, the overall importance of dew point. As we know, condensing boilers, we need to see water temperatures coming back at around 130 or less in order to have that water vapor condense in the heat exchanger. Once you're above 130, above 135, it's just not going to condense, no matter what the manufacturer tells you. Below 130, we will condense, but there's some critical conditions, and we'll get into those later. Here's just a very simple diagram of a heating system, and we see again, we need to get that return water temperature down to at or below 130 in order for condensing to occur. Lots of avenues to get into that. That would be something part of a much larger discussion. For the 20 minutes that we have here, we want to focus on the newest developments, the high turndown. Here we have the diagram on the left-hand side shows the 5-to-1 turndown, which has been quite industry common for the last 5 to 10 years. 1,000,000 BTU boiler runs down to about 200,000 and has the ability to ramp up back up to 1 million. 20-to-1. Now we can run a 1,000,000 BTU boiler down to 50,000 BTU. So really have a very much broader operating range. The benefits of this are several. First of all, as we all know, heating systems are always designed for our design day. They hardly ever operate there. Typically there's some redundancy in the system, so there's excess capacity. So a boiler will hardly ever run near that full fire condition. So in these larger commercial systems where we have 2, 3, 4 boilers in operation, we could have two, 3 boilers operating at 10 to 1 turn down at 100,000, 150, 200,000 BTUs, doing the bulk of the heating. And then as the load increases, we'll have another unit come on operating at this very low input level, really ensuring max efficiency. And what it also does by having these high turn down boilers is the equipment will cycle far less, because the boilers can actually operate in harmony with the heat loss that the building is experiencing. So reducing off-cycle losses, reducing wear and tear of the mechanical components. And again, with the higher turn down, we also achieve the higher efficiency. I'm sure many people have seen this curve, which shows the thermal efficiency of a commercial boiler as a function of return water temperature. The blue curve basically representing the boiler operating at full fire. The yellow-orange curve, the top curve, representing the boiler operating at 5% input capacity. And we see here, depending on return water temperature, we're seeing anywhere between a 1 over 2% efficiency gain just by having this turn down. So again, by having 20 to 1 turn down, have a few units in the system operating at these low firing rates, even if it's not 5, but it could be 10% turn down or 10% firing rate, we'll be picking up 1.5 to 2% efficiency gain throughout that condensation range. Basically what's happening here when we're running at these very high turn downs, of course, we're burning a lot less fuel, we're burning a lot less natural gas. The flue products will spend a lot more time inside the heat exchanger for heat transfer to take place. And provided, and this is the big provided, we maintain similar levels of excess air, and we'll get into that shortly, we can achieve these increases in efficiency because of the higher residence time, the more time that these flue gases spend inside the heat exchanger. Talking a little bit about combustion, what we see here is the overall combustion in a simplified manner of natural gas. Natural gas is primarily methane, and we have then 1 molecule of natural gas combining with 2 molecules here on the lower right, 2 molecules of O2 combined to produce CO2 and the water vapor. Non-condensing boilers, all the water vapor goes up the chimney. On condensing boilers, we're looking to reclaim that water vapor as much as possible, turn it back into condensate, and turn that latent heat into usable heat by transferring it to the boiler water. Looking at this chart, one thing that is very obvious too is we see 1 molecule of natural gas, we see 2 sets of molecules of hydrogen, but we have a tremendous amount of nitrogen. As we know, this air is about 80% nitrogen, 20% oxygen, roughly. So we have all this nitrogen that comes along into the combustion zone, rides along, and goes back up the chimney. In case of excess air, where we do need some excess air, and we'll talk about that shortly, we'll have additional oxygen, we'll have additional nitrogen molecules traveling along through the combustion chamber. And basically what they really do is they dilute our water vapor. So it's like in the middle of summer when it's 95% humidity, if you now have bring excess air into a room, provided it's clean, dry air, you're actually dehumidifying the room. Well, that's actually what excess air does. It dehumidifies the water vapor going up the chimney, and we'll get into its effects in a moment. Some of the challenges in terms of natural gas combustion, we want CO, we want to minimize CO, we want to minimize NOx, and we have excess air available. We need some excess air, as I noticed, 78% nitrogen, about 21% O2, a little bit of argon. We need some excess air to really limit that CO production. Another thing that we need to watch out for is NOx levels. They will increase very rapidly when the flame temperatures, the temperatures with which combustion occur, as they go up. In all modern condensing packages, condensing boilers, all these boilers use what they call premix burners, pre-mixed burners indicate that the fuel and the air are mixed at a microscopic level, at a molecular level. They're uniformly distributed, so you have a better chance of a cleaner burn, but we still need some excess air to suppress NOx levels. The third bullet is really the key driver, and we'll focus on that through most of the rest of the presentation. Is condensing operation is negatively affected by excess air. Just as I mentioned, an example of middle of the summer when we get hot, muggy air, adding some dry air to that mixture lowers the moisture level. That's exactly when we have excess air, a lot of excess air in the boiler. It lowers the moisture level of the water vapor, and we can only then result in condensing at lower temperatures. Finally, of course, we want reliable operation. We want low emission levels, and all these are a must. O2 trim, and we'll talk about O2 trim towards the end, is one of the key drivers that can enhance low emission levels, can ensure low emission levels, can improve and enhance reliable operation. As we now, with O2 trim, we can make some fine-tuned adjustments and make sure that during the operating phase of the boiler, the combustion processes run as optimized as possible. Here's a little bit of chart. I want to talk a little bit about this one. This just talks about the concept of dew point control. Again, it's the moisture level of the flue gases. Typically with natural gas combustion, we're looking at our CO2 anywhere between 8 to 10%. At 10%, now we have 10%, we have less excess air, and our flue gases, our water vapor in the boiler will actually condense at about 131 degrees. As we lower our CO2, meaning we add some additional excess air to our combustion process, and we achieve a CO2 of 8%, now our dew point, because we're diluting our flue gases, our dew point now drops down to 122. And that's physics. So from a combustion perspective, we want to try to maintain our CO2s as high as possible, without resulting into excessive CO or NOx levels, but really make sure that we keep our CO2s higher, drive up to a higher dew point, and so we can achieve more condensation. Once our CO2 starts drifting downward, we're lowering our dew point. Again, that's the temperature at which the water vapor will start to condense in the boiler, and we're going to see less condensation, and therefore our boiler will be less efficient. So it's really about dew point control, is really about monitoring your CO2 levels and making sure you keep them as high as possible. Of course, when the boiler is initially installed in the field and is commissioned, part of the commissioning process is, the burner is set up and gas pressure is checked at low fire, high fire, and people look at CO2 levels. At this point, one really needs to be very careful and examine the fine print of manufacturers' manuals to really note what are they looking at, what are the recommended settings for high fire settings and for low fire settings. So here's one manufacturer basically has a high fire setting at 9%, plus or minus 0.2, a low fire between 8 to 9.2. Some other manufacturers, depending on their setup, they list CO2 levels anywhere between high 2% up to the high 88%. So these are some of the critical things that you need to monitor when the combustion specialist needs to monitor, and you as a specifying engineer or contractor may want to take a look at in terms of specifying equipment so that the end user will indeed receive the performance of the equipment that was expected. Here again, we see these different levels of CO2 level recommended by different manufacturers at the time of startup of their equipment. What I want to do next is talk a little bit more about the O2 trim systems. Lars came out with an O2 trim system last year. We launched it initially on our Water 2 product line. running from 1 million to 4 million, or 1.6 up to 4 million, both boiler version as well as a volume water heater version, giving us a 20 to 1 turn down. And we just recently introduced it on our fire tube product line as well, running from 1 million up to 3 million. Here we have independent control of air and fuel delivery to the burner. We, as most people do, they use most manufacturers use a variable speed blower for high turn down operation, using a premixed burner in order to distribute out the fuel in air and have as large a surface as possible for combustion, get clean combustion. The O2 trim system that Lars is deploying is a continuous O2 trim sensing. So after initial startup, the trim function will become active and it will trim as is necessary. In addition, most trim manufacturers that offer O2 trim also have a periodic calibration of the trim function where, say, once a day or once a week, the unit engages without operation, without burning gas. The unit basically just checks for O2 levels, and the O2 levels would basically be equal to ambient O2 levels, ensuring calibration of the equipment. Here we see the effect of O2 trim. What I'd like you to look at here, the key I'd like you to focus on here is the red line, which is basically representing the CO2 levels with the trim function turned off. And we see here that the O2 trim system deployed by Lars is basically setting up, looking at fuel and air settings at 9 points along the curve from low fire to full fire. And we see here that with the trim function disengaged, our CO2 levels run between about 7.7 up to a little over 9%. Okay, a little higher on the low end, a little lower on the high end. We then engage the O2 trim function and let the equipment basically auto calibrate itself. We now see that after a short period of time, we see that the CO2 level throughout the entire range hovers around 9%. Okay, so systems without O2 trim, they can be set up. Maybe they might be set up around 9%, but depending upon environmental conditions, and we'll talk about some of those conditions, they will not always operate there. Whereas systems equipped with O2 trim capability, they will, except during the initial startup phase, but once they run in a steady state condition, the O2 trim will engage and make any necessary corrections necessary to ensure peak performance on the equipment. Here's a gas train with a gas solenoid, gas regulator and shutoff. There's also a fuel damper, and with that we have very fine-tuned control over the fuel delivery. Like I said, there's along 9 points of the curve. These are factory calibrated, and then in between the curves, the internal control system will then basically make the necessary fine-tuned adjustments on each of these to ensure that high efficiency along the entire curve. Then the gas mixture is then brought into the mixer, a fuel air mixer. The combustion air is being pulled in through the blower. Fuel and air is mixed in a mixer, going through the blower, or through the blower is then injected into the premix burner, where the fuel mixture ratio will then emanate from the outside surface and then burn on the outer surface of the premix burner. The blower speed, during the O2 trim function, the blower speed will make slight modifications to make the necessary adjustments on the CO2 or on the O2. Here we see the O2 sensor itself. This is on our water tube product, where the O2 sensor is in the primary heat exchanger shroud, sensing flue gases at an intermediate temperature, but really sensing the O2. It's an proven automotive grade O2 sensor. It's been used in the automotive industry for many years. It does continuous sensing on the large system. O2 sensor becomes active after 2-minute warm-up period, and then the sensor provides continuous feedback on the combustion characteristics and trims as is necessary. We have the 9 to 10 points along the fuel air curve with preset O2 values on each of the range, and then it makes the necessary fine-tuned adjustments. Another system that's on the market, where we have the O2 sensor. In this case, the O2 sensor is in the combustion chamber, again sensing a signal back to the boiler controller, which in turn makes a fine-tuned adjustment on the blower. So here we see, in a little bit more detail, here we have what's called the air fuel valve, again, where the air and the fuel are mixed together and then being sent out to the blower, being pulled from the blower and then sent out to the burner. Here we see a couple of curves that really show the effect of excess air. The chart here on the left is basically no excess air. That's called stoichiometric combustion. That's the ideal world. That's where academia lives in, but the real world, we need some excess air to handle and make sure that we don't have rampant CO or reduce our NOx levels. And then, of course, as the excess air increases, at the same time, the CO2 decreases. So some people talk about CO2, other people talk about O2. They're inversely proportional. On the right-hand side here, we see again this graph of the CO2 level and the effect that the CO2 level has, the dew point has, how the dew point changes with different CO2 percentages. So 10.5, that's about stoichiometric. We could get condensing at about 135, but of course that's because the compactness of the heat exchanger imperfections. We typically need to run around 10 or lower than 10, 9.5. We'll see condensing around 130. But then once the CO2 temperature really starts dropping below 7%, you can see that the dew point will now drop to about 110, 115. So again, we really need to control the amount of excess air to reinsure that we have condensing occurring more around the 130 range than below the 120 degree range. Some other benefits of the large system: we have continuous O2 monitoring. This O2 trim is now available both on our water tube as well as on our fire tube boilers. So some other benefits is that a lot of boilers are being started up in the summertime, outdoor temperatures, especially if combustion air is being pulled in from the outside. It's being set up with combustion air being 80 degrees, and then the boiler shuts down, after startup, because the boiler may only need to run during the heating season. Well, heating time runs and comes, and now the outdoor temperature might be 20, 40, 30, 40, 20, 30, 10 degrees. What happens as the outdoor temperature goes down? The air becomes more dense. So even though the boiler initially was set up to run at 85, 95% efficiency, if now the outdoor temperature is in the winter time, it's colder, is more dense, the blower doesn't know. The blower is still going to move just as fast in a normal condition. However, what the O2 trim sensor will do is say, hey, I'm seeing too much air. It's going to slow down the burner, and the burner will basically adjust, or the O2 trim system will basically adjust for the change in outdoor temperature and ensure that we're continuing to operate at that 95% level. Another issue that might develop, maybe have some combustion air dampers, and maybe somewhere these combustion air dampers, they start having a failure, they don't fully open, they maybe don't fully close. So now the burner might not be it's pulling combustion air from the mechanical room. It may not, the blower, especially as they start running more at full capacity, they may not be getting enough air, and we could be becoming fuel rich, which would result in high CO levels. Well, the O2 trim detector will sense this, and again, will make an adjustment on the blower speed. If at some point in time we run in a situation where we're out of adjustment, we can only accommodate an engineer for so much. If there's no air available, there's no air available. The O2 trim sensor will first allow the system to be more flexible and accommodate the situation, but then there will be a diagnostics on the system that will say, hey, Houston, we have an issue here. Something needs to happen here before, and the diagnostic signal will come out before we have a shutdown on the equipment. Whereas with systems without conventional O2 or without O2 trim, they would simply try, they would not work anymore, and there would be a service call. O2 trim, the system will continue to operate for a certain period of time and provide diagnostics before we actually have an emergency situation. So it's another benefit by having O2 trim systems available. Just to wrap up here, just a couple critical steps here for high efficiency operation. Really got to consider your design conditions. We kind of skipped over that part, but I believe there's a meeting coming up in a few weeks that Greg is putting on, and we can get talking about some more of those details. Also, we want to match our boiler operating system to the system design. Again, this looks at boiler piping, primary, secondary versus variable primary piping. We would talk about the benefits of high turndown boilers, deploying N+1 equipment selection for redundancy. So some of these items are more topics we did kind of touched on them very lightly here. But I think my key takeaway is that by considering O2 trim capability, O2 trim will really give O2 trim and looking at what the different manufacturers' requirements are or suggested setups requirements are for the systems will allow you to have optimized dew point control, minimize the amount of excess air, improve overall uptime of the boiler plant, and along with the O2 trim, there's also some advanced diagnostics that will come along that will give the property manager the capability to see when things are starting to go wrong before the actually equipment starts shutting down. So it's kind of like the orange light in your car. You know that you got to take it to the garage first, to the red light that simply says, okay, sorry, I'm going to shut down. So there's a lot of benefit to the O2 trim, not just the efficiency, but also the improvement in uptime reliability along with the advanced diagnostics. Okay. I want to thank you, and I think Greg has a few things that he's got a giveaway coming up, and then we'll address some, do some Q&A.
That's right. All right. Hey, can everyone hear me? Lou, can you hear me?
Yes, I can.
Great. All right. So Lou, thank you. That was really great. We learned a whole lot there. We are going to get to the Q&A in just a minute. What I want to do is just advance real quick, let you guys know a couple of upcoming webinars that we've got coming up. So we still got some time. We're gonna so the presentation part is over. We will continue for the Q&A. We'll be on here till maybe about 11 o'clock. Upcoming webinars though. So based upon some actual input from everyone, when they saw this presentation coming up, we actually got a lot of requests asking if this would be a PDH level course. So we did ask Dr. Lou if he could come back, and he will be coming back on the 10th. So schedule on your calendars, June 10th, we will have an invite going out, and we will be doing a webinar-based PDH that's going to be available. All right, so keep your eyes peeled for that one. We also have two other PDHs, or I'm sorry, not PDHs, forgive me. We got a couple other webinars coming up, so we're staying pretty busy here. We got on June 17th, Ken Resnick of Rath Associates will be presenting on combustion analysis. TPI is the product of choice. And then on the 25th, Kevin Woodworth of US Pump will be presenting on the iLevel. The iLevel is a new control system that allows you to ditch the problem-prone floats that we're all familiar with. All right, so that's what's coming up, so keep your eyes peeled for that. So aside from that, let me just jump over to the poll. So like I mentioned, I'm just going to put this up there for you all. So like I mentioned, Rath Associates, we really want to do our part during this whole pandemic. We really want to make sure that, we're helping out wherever we can. So we'd ask that you guys could all jump on here and respond to the poll. Just going to keep my eyes peeled, see how this is all coming along. So everyone who is on here, we're going to keep this up for about a minute or so. So just chime in, let us know who you'd like us to send $500 to. So like we said, so far we've donated just about $3,000 during this pandemic to a variety of charities and frontline kind of people there. Just trying to do our part to help these people out. Just get some money out where it can really do the most amount of good. So just going to keep this open for maybe another 15, 20 seconds to see maybe about half of you guys have voted. While everyone's still voting and everything, guys, we have a whole bunch of questions that have flown in, so please do me a favor. Click on that little question bar and throw your question out there. It could be a question, it could be a thought, it could be on the topic, it could be on LARs, it could be on water heaters in general, boilers in general. We got a doctor of thermal efficiency here, thermal combustion, so chances are he'll be able to answer your question. So get those questions rolling in, and we'll start addressing them. I'm going to close this out in about another 5 seconds. Keep voting, everyone. Thank you for doing so. And we are closed. Just so you all know, it looks like, I think probably a pretty good choice there. Probably makes the most amount of sense. We've donated to them before as well, the COVID-19 Emergency Relief Fund. So we will get that check out, and we appreciate everyone chiming in there and helping out. So without further ado, let's get into the questions. I'm going to be firing the questions out there. We've also got Bruce Drummond of Rath Associates on the line with us as well. So the two of us are going to be moderating these questions back and forth. Bruce, you want to, if you're available there, I don't know if you have a question that you've seen here that you want to jump out with.
I have a good question for Lou regarding some maintenance. Lou, how often do these sensors require calibration or recalibration?
Well, like I said, the O2 sensor itself recalibrates itself on I think in the LAR system on a daily basis. Most manufacturers have them on a daily basis. I've had a Mercedes-Benz now for what, 15 years. I've not replaced my O2 sensor on that car yet. So in terms of, the calibration occurs on a daily basis. In terms of longevity on the O2 sensor, it's like I said, on my diesel, and I've got close to 300,000 miles on a car. I've not replaced my O2 sensor yet, so I don't see that happening on the boilers either.
Okay, thank you.
All right, Lou. So we'll just kind of go back and forth. We'll just kind of crossfire you. What about altitude? How does altitude affect the O2 trim system?
Altitude is that's a good question. Of course, as you go at altitude, the air gets thinner, and the blower will, in order to get the same capacity, the blower will need to basically need to upsize the boiler to some extent, or basically need to upsize the boiler to some extent because of the higher altitude, the gas pressures are less as well. But the O2 trim itself, it's looking at O2. It's looking at the O2 sensor O2 levels. So it will ensure that we maintain the right fuel to air ratio and make the necessary adjustments as has been programmed into the control system. So the O2 trim function will work equally well at high altitude as at sea level conditions. One we'll need to do is upsize the equipment some because of atmospheric conditions. At 9,000 feet of elevation, instead of being the atmospheric pressure being 14.7 psi, I think it might be around 12 psi. So that's nothing you can do about that. So the blower will bring in less fuel, or excuse me, the blower per rotation will bring in less air, and we need to bring in the commensurate fewer amount of gas as well and maintain that fuel air ratio. But the O2 trim, so once the basic setup has been done on the equipment, the O2 trim sensor will ensure again and do that fine-tuned operation.
Right. So it sounds like as far as the O2 trim portion of the whole operation goes, it is not affected. Just general practice. If you're dealing with a high altitude application, you got to kind of take that into consideration just for sizing.
Correct.
All right. Thanks, Bruce. You got another one?
Yeah, Lou, the table that you had up in the presentation, table 9A, what boiler was that related to?
Let me just jump in. I don't think we want to necessarily call anyone out in particular, but I will jump back to that table if you don't mind. Sorry to just jump in, guys. It's just I don't want to do that necessarily. But listen, if you look around, if you dig through some IO manuals, you'll find this, whether it be this one or another competitor. Um, the key thing that I actually wanted to kind of point out was if you look at the various CO2 levels, so you'll see, the higher values like Lou was mentioning in the 8 to 9 range, but in this particular unit, it can be as low as 1.3. So if you just kind of take a look at this chart, 1.3 is extremely low. It's probably somewhere around here, if everyone can see my screen. So what this is telling us is that for that particular unit at low fire, you would need a return water temperature, and Lou, correct me if I'm wrong, maybe jump in at any point, but you would need a return water temperature, I would believe, of maybe about 70 degrees to even begin condensing. Maybe you could just kind of chime in on that.
Yeah, I mean, it's once you get to those CO2 levels, it's any chance of condensation is really non-existent. Because another way of looking at it is, like I said, just consider damp air. It's beautiful weather up here in New Hampshire. It's summer's here. It's not hot and muggy yet, but once we get into August, the moisture level goes up significantly, and once you get your AC when you get your AC running in your house, you may have got moisture starting to build up on your condenser unit. That's really the same thing is really happening inside of a boiler. So as you bring in more excess air, you're really diluting the water vapor, and you got to bring your water temperatures much lower. Yeah, exactly. That's about 70 degrees. So that boiler will not condense under those operating conditions. I mean, unless on initial startup, when you first start the system up, it will condense very nicely. But then once you get over 100 degrees, it's just not going to condense. So it's really looking at the details of those CO2 levels during low fire and high fire. What are those? Look deep down in the manual and make sure that they are in the 8 to 9.5% range to really make sure that we know that we're going to be condensing in the 120 to the 130 degree range.
Great. All right. Thank you. Hey, here's another question. Why, maybe a pretty simple one. Why measure O2 as opposed to CO2? It sounds like we're talking a lot about CO2, but then we measure O2. Why would you select one over the other?
Good question. I think they started out measuring O2. I don't know the exact reason why that is, but they are, if you have a lot of O2, then your CO2, they're inversely proportional to each other, as I indicated on that one graph. I think it may just have something to do with the way to detect the O2 molecules, but I don't know exactly the real reason why there are O2 sensors versus CO2 sensors in these engines. Because it's an offshoot of the automotive industry.
All right, but yeah, it sounds like it's interchangeable because, like you said, they are inversely related to each other. So you measure one, you kind of know the other one automatically.
Exactly. Oh yeah, you measure one, you know the other. Exactly. Yep. Another reason I think we're going with the O2 is we all know we're going to have CO2 in the exhaust, and the O2 is a direct indication of the amount of excess air. Because again, if you have a stoichiometric combustion, so there's no excess air going along, then that would mean nothing to sense. So we do want to have a little bit of excess air, so that I think therefore probably people settled on using the O2 sensor versus a CO2 sensor.
All right. Another question here: Does the condensation transfer to the heat exchanger before it leaves the boiler or water heater? Let me actually, so I asked that question out there, and I just want to maybe reiterate to everyone, we're kind of using the term boiler a lot. We're using the term interchangeably So Lars offers both boilers and water heaters. So like, for instance, they have the Magnatherm that's offered as both a boiler or a water heater. They've got the Pennant, boiler, water heater. So their entire range of products are both boilers and water heaters. And so, forgive us if we're saying boiler exclusively, but water heater included. Someone had asked, why would we need a boiler running in the summer? That's we're not really referencing that scenario necessarily. I mean, maybe in an industrial application you might need that, but we are just kind of using the term interchangeably. So just wanted to put that little note out there. But Lou, maybe you could just jump back on that question. Does the condensation transfer to the heat exchanger before it leaves the boiler?
No, that's a good question. Yes, the vast majority of the condensation, of course, occurs inside the boiler or the heat exchanger, because that's where we have the flue gases. That's where we have, on the other side of the steel surface, we have either the domestic water or the closed loop boiler water. So that's where the heat transfer takes place. And the condensate will then basically settle down and condense down on the water back surface as part of the heat exchanger. We will have a small, of course, the exhaust gases, once they come out of the boiler, they need to go up the venting system, either vertical or horizontal, and there'll be some additional heat losses in the venting system, and there will be some flue gas or some condensate that will be draining back through the venting system back to the boiler, and then everything will then be drained away through the condensate drain, and most likely the condensate should be treated, and then it can be disposed of. But yeah, I'd say 90% of the condensate would occur in the boiler and a small percentage in the venting. Also keep in mind, especially on volume water heater applications where we have maybe a set point of 120, 130. I mean, those are extremely excellent conditions for condensing operation, because you're always in the condensing range. Whereas in space heating applications, you look at the return water temperature. So you have, in the middle of winter, you may have a somewhat higher supply temperature. Depending on the application, that return temperature may vary. But volume water applications, you're always in the jackpot. You're in condensing mode year round under virtually all applications.
Lou, I got a question here that says, how can the BMS support the boiler system to improve efficiency? Possibly return water temperature control?
Yeah, the way to improve efficiency is one of the key ingredients is return water temperature control, and that of course is dependent upon system layout, and some of those things, we'll get into those details in a pretty good level of detail in I think next week or in 2 weeks. So the BMS, really slowing down pumps. Interestingly enough, when we started in this industry, I worked for a number of years for a German-based manufacturer. Most heating systems in Germany are based on a 36-degree delta T, whereas most heating systems in the US have traditionally been designed around a 20-degree delta T. So in the US, we love pumps, we love big pipes. In Europe, they go with smaller pumps, smaller pipes. They go with larger radiation. They basically try to get more heat out of a given piece of baseboard or panel radiator, or what you may have. And I know it's a little bit of a sidebar, but especially in Germany, the heating industry and the design of heating systems has been very heavily regulated. Of course, after World War II, they had to rebuild the country from scratch. So whatever steam was in Germany prior to World War II was not reinstalled. They basically went to hydronic heating. And then in the early 70s, during the oil crisis, many companies made a direct leap, and from a government requirement standpoint, outdoor reset became the law of the land in Germany by the mid-70s. So running boilers down at low water temperatures, even though these boilers were not condensing boilers, but then as one realized that, hey, and they also transitioning from coal to oil to gas, then the condensing boilers started finding their way out in the marketplace in the early 80s. And as they say, the rest is history. But yes, really in Germany, they went from 190 to 160 design temperatures. And then in the late to mid 90s, when condensing equipment became very prevalent, they basically had a requirement where new systems, new buildings had to be designed on a maximum supply temperature of 122 and a return temperature of about 110 or 105. So you're always condensing, you're always going to be running 95 plus. You're just going to have a lot more baseboard or panel radiators. At the same time, they also basically implemented much stricter standards in terms of building envelope insulation, triple pane windows, and really reducing the overall heat loss on buildings themselves. But it's really been interesting to see that transition in efficiency requirements, especially within Germany, and how that has changed the entire building industry, and actually also changed the boiler industry. I remember being at a meeting a number of years ago where, years prior, people were always talking about the heat load and looking at on residential systems. They were looking at, okay, how big is the house? What's the total BTU load on that house from a heating perspective? Well, at that meeting, they weren't really talking about the heating load on the home anymore. They were talking about the maximum domestic load, because the envelope of the building had been reduced, had been insulated so well that the heat load really was no longer the maximum load on the boiler. It was really the domestic, the instantaneous domestic load, and a lot of combi boilers were then being used to provide both space heating as well as domestic at the same, with one appliance. But because the progress in the building code, the heat load had become a much smaller factor. A little bit of some anecdotal information, but we'll talk about those things a lot more in the next few weeks.
And no worries, that's all great. I got another question here. All right, so even if a tiny percentage of condensation will happen in the flue and a majority is inside the boiler, does it make sense to use a single wall flue venting system?
Does it make sense to make a single wall flue venting system? Well, I mean, if depending on exhaust temperatures, CPVC, polypropylene, or stainless steel venting, single wall venting can be used. Just keep in mind that the exhaust temperature on these condensing boilers will typically be well below 200 degrees. And especially when you run them in condensing mode, your exhaust temperature may actually be less than your supply temperature in many cases. So yeah, a lot of these equipment can also run in a positive pressure vent application. So you can, instead of having your large 12, 16-inch diameter negative draft venting systems, you can reduce your venting size significantly and save on cost on the overall installation.
All right, great. Got another question here. Is a mass air flow sensor of sort or type included and utilized for monitoring intake combustion air, or is this an algorithm utilized for use with O2 trim along with intake air sensor?
No, the O2 trim sensor, located in the boiler itself, measures the O2. Of course, it requires that every appliance, every boiler or water heater is factory set based on the conditions at the factory here, with the 10.9 point curve from low fire to high fire. There's no mass flow sensor in the air intake, so it's not like we're measuring how much either the volumetric or the mass flow of air going into the boiler, but we do set the gas pressure, and the gas pressure and the units are calibrated here when we ship them, and the gas pressure is set at the field, and that will basically set the fuel flow rate, and then the 9 or 10 point curve of the fuel air ratio indirectly regulates and sets then the mass flow rate on the combustion air.
All right, thank you. Another question, the same person there. Upon initial commissioning with a combustion analyzer and or annual service, I would assume that O2 trim needs to be shut off. Is that something easily done with the Lars link control on the magnetherm that utilize? Oh, there's more to this. I gotta make it bigger. So is that something that's, I guess, all right, so answer that first bit of the question, and then is that something easily done through the control?
Yes, yes, you can go right into the menu and just enable or disenable the O2 trim function. Yep. Actually, you know, I was in just a kind of anecdotal story too. I was in the lab a couple of months ago, and talking to one of the lab technicians, like, well, you go, what are you doing here? It's like, well, you know, I'm testing the boiler, running different return water temperatures. I go, oh, that's interesting. And so he was running it with the O2 trim off, and we're getting, you know, certain CO2 levels. And then he goes, now I can turn the O2 trim on. You know, the O2, the CO2 was 8.4, 8.5, whatever it was. He goes, I'm going to turn the O2 trim on. So nothing else changed. The equipment was running. He engaged the O2 trim sensor. You know, it just took a few minutes for it to kind of go through its warm-up process, and then it became active. And then within 5 minutes, we saw that CO2 move up to 9%. So yes, you can turn it on, you can turn it off on the control system very easily.
All right, great. That's great news. All right, I got another great question here, very interesting one, and you'd probably be just the guy to answer it. So this person has asked or says, I'm starting to see condensing boilers coming out with dual return inlets, high and low temp, to optimize efficiency. The low temp usually deals with conditioning outside air. The higher inlet is often used for heat loads decoupled for ventilation. I haven't seen much literature to demonstrate this actually has an impact on efficiency. Do you have any opinions on this?
I do have an opinion on it. I mean, I think the critical part there is really just to ensure that the application is the correct for it, and that it, you know, one really needs to make sure that the whole system is properly designed for it under all operating conditions. You know, there can be some benefits, but it's part of the entire package. You know, it's everything needs to be aligned. Everything must be done properly in order to reap the full the presented benefits of that capability. It does require, of course, additional piping. It may require some, you know, additional pumping. So one would really need to take a look at, okay, what are the additional cost features in it, or does it really, can we anticipate and can we reliably expect the expected efficiency gain on that application? I think one area where I see a tremendous opportunity with condensing boilers is really condensing volume water heaters. Because typically, you know, water might be stored at even if it's semi-instantaneous or with a storage system. You know, a storage system will store the water at 140, but we know that there might be a recirculation line involved, so that, you know, that has some return temperature. But by golly, we always have 60, 70, even if we got 80-degree water coming into the boiler, and we got 120, 130, 140 going out. I mean, that's 95%, 96, 97% year round. You know, whereas on heating equipment, you know, you do have the shoulder season where lots of opportunity for condensing, but again, depending on the system layout, peak winter conditions, you know, if you need 160 out in the system, you need 160 or 180 out in the system with a 20-degree return, you know, 140, 160 return. Nobody will condense at 160. Okay, so volume water heater is really, I think, a unique, very great opportunity for massive amount of condensation and really getting peak efficiency benefits.
All right, yeah, and you know, I'll kind of jump on that as well. So I mean, you point out like a really good point, right? I mean, so yeah, there are potential, you know, if done exactly right and done well, you know, of course there could be an efficiency gain. But you know, you pointed out that it's an entire system and it's entire, you know, all the piping and all the controls that get included in this, and then, you know, the controls that are built into a unit that would, you know, operate this way. You know, does the efficiency gained actually outweigh the cost of utilizing this kind of system. So this is the kind of thing that really has to be weighed out. And in today's climate, I mean, with the markets going up and down, and God knows how much money's available, you really have to take these all these thoughts into consideration. And and another thing that kind of is often overlooked, I would say maybe by the engineering community, is again the full picture. And one of the things, a little, I guess, plug for us that I'll throw out there, is that the way that Rath Associates goes to market in our territory is we have a large array of certified service contractors who are factory trained and get updated training regularly up at the factory as well as at our own facility in Farmingdale. And what that offers to the engineer and to the facility manager and the owner is a peace of mind that there are a wide array of people who know how to solve the problems. If you don't like one, you call up the next guy. You're not locked into, Rath Associates in our service department and when we're available. So there's a lot of people that you can get service contracts with. We have parts available at our own facility and at many of our major wholesalers all throughout the tri-state area. So, just got to get that plug out there because it is a very important and often overlooked piece of the puzzle. You don't want to get that phone call saying, the unit that has been installed here, I can't get a guy who understands how to service this thing. I can't get anyone to fix this. I can't get parts. These boilers and water heaters are getting much more intricate, and they're like BMWs. You have to take them in, or you really should get them not really taken in, but you should get them serviced, right? Get them looked at annually, do a combustion analysis test. And again, we're offering, we have a wide array of people who know how to do this. And again, in a couple of weeks, we're offering a combustion analysis test because we recognize how important this is. So just gotta get that little plug out there. Bruce, I think you got another question there?
I do, and we'll stay on that combustion analysis topic real quick. Question comes in, why sometimes when I test a boiler on low fire, it produces high CO?
Why got low CO? We may have on low fire, of course, there's a lot less heat that's being available. So during the detailed combustion process where we have methane, CH4, so you got a carbon, 4 hydrogens around it, the hydrogens kind of fall off, and then the oxygen kind of marries up to a CO. Initially, in the initial phase, CO is first formed, and then an oxygen molecule or atom is added to that CO combination to create CO2. So therefore, when you run at low input levels, combustion chamber is still the same size. We have now a lot fewer fuel molecules in there, a lot less air, and there may not be, not all the air molecules at that point in time may necessarily match up with a carbon molecule. So there could be potential for some higher CO levels during that low fire operation, just because of we still have the same amount of space, it's just of our fewer molecules, so there's less of a chance for two oxygens kind of partner up and team up with a carbon molecule to create CO2, and we may get some excess CO forming during these low fire conditions.
Thank you, Lou.
Hey, so Lou, I got just a general question in terms of time for you. So we still have a couple questions that are here. Do you have time? Because it's a little past 11 now, and we still have a bunch of attendees on. Like I said, a couple questions still rolling in. So do you have another 10, 15 minutes or?
No, I got about another five
Okay.
to 8 minutes. Yep.
Great, thank you. All right, so I guess another question I've got here is just a bit more of a general one. Water tube versus fire tube. People seem to be in different camps. Is one better than the other? Is it application driven? I guess your thoughts on it.
Yeah, gotcha. No, that's a very good question. That's a very, very good question. I mean, water tube boilers typically have somewhat more requirements in terms of flow rate. So there's more stringent requirements in terms of minimum, maximum flow rate through the unit, because we really have water flowing through the inside of the tube. We got the heat impinging on the outside, and if the flow is not sufficient, we can have scale and deposits kind of build up on the inside. So the water tube boilers or volume water heaters, you know, they work great in primary, secondary applications or in straight volume water heating applications. Again, if the water hardness in a potable application is harder, then of course we need to account for that by installing a larger and properly sized pump. Fire tube boilers, just by their design, they're strictly used for boiler application, not for volume water applications, because you know a fire tube boiler cannot handle fresh water. The fresh water, with basically the sediment would build up underneath the tube sheet over time, and you know that could lead to catastrophic issues. But the fire tube, because they're designed, they have more water in them. They are not as flow dependent, so they lend themselves exceptionally well for larger delta T systems. A variable primary flow without secondary piping. So you could have 3 or 4 water tubes in a system, and then ideally you want to, or especially when you have more than 2, you want to put a motorized valve on each boiler so that only those boilers that are actually actively running for that system pump will pump through those boilers. And as the heat load increases and we need to bring on number 3 or number 4 boiler, we simply open up the motorized valve and now divert that increasing system loop flow. Instead of running through 2 boilers, we may run it through 3 or 4 boilers. So they each have their own spot in the market. You know, of course, water tube is ideal for volume water applications, and you know, water tube boilers are also fine in primary, secondary applications. You know, maybe it's a system change out where there used to be piping arrangement was primary, secondary. Well, you know, you can just slide water tube boilers in and keep everything else as the system is. Keep, you know, maintain the rest of the system in place. Fire tube boilers, you know, give you a little bit more system design flexibility. You can run some larger delta T's on the system, and you can keep the near boiler piping and complexity to a minimum. So yeah, they both each have their place in the market.
All right, great, thanks. Bruce, do you have any other questions you want to fire over at him?
I got one last question here. Probably the last 2 or 3 minutes of your time. I have a gentleman who presented a little bit of a situational question for you, Lou, if you don't mind.
Sure.
So he's got an existing heating system about 5 years old. He's asking what VFD controlling strategy for the boiler pump is best to utilize. Oops, sorry, I just lost the question. Best to utilize for a Magnatherm MGH 3000. Says the boiler pump loops VFDs are working on maximum speed now, and the primary design loop temperature is 140. If you need me to read that again, no problem.
Oh, let me just get a piece of paper, because as a typical engineer, I need to have a piece of paper when I hear these types of things.
Sure. Let me know when you're ready.
Yeah, go ahead.
All right. So he's asking about the best VFD control strategy to for the boiler pump for a Magnatherm MGH 3000. He's got VFDs are working on max speed, and the primary system loop design temperature is 140.
Okay. So each boiler is basically injecting into the main loop.
Yes.
Yeah. And do we know what the return temperature is, or the delta T on the system?
He did not specify that, Lou, to be honest. I can
Okay.
try and ask him right now
Hey,
if you'd like.
Maybe what we'll do is we'll maybe take this one offline. It looks like a little bit more in depth. Sounds like we're getting pen to pad,
Yeah.
probably calculators coming out.
Yeah.
So,
I just want to throw something out there without having the details, you know?
No problem. Fully understood. We'll try and get back to him with the answer to his question. Maybe we can communicate and help him that way.
Yep.
Right. All right. So I think you know, that kind of does it for our time. So I just want to thank everyone for joining us. Really, love having all you with us. We had a great attendance today, and a little reminder. This is basically almost a little sneak peek, a little taste of on June 10th, we're going to do an actual PDH on this topic. So, come back if you're an engineer or someone who can get these PDH credits. Come back and we'll make sure to get you, your certificate. So thank you for the questions, Dr. Liu. Really appreciate you giving us the time and really giving a great presentation here. And not to put you on the spot, but do you have any closing words or thoughts on this topic or anything else?
Like as in many cases, the devil's in the details. So if you're really looking to have peak efficiency on a commercial application, whether it's volume hot water or space heating, just don't just look at the efficiency number, but look at the details. I think I gave some information in terms of what you should be looking for, and don't underestimate the benefits of O2 trim, not just from an efficiency perspective, but also from an uptime, reliability, and flexibility perspective.
All right, great. And I guess a little closing note also. So Lars boilers and water heaters, we have everything from 50,000 BTUs all the way up to 4 million and climbing. We have condensing and non-condensing. We've got every kind of unit for the different application you require. Right on their website, you can see right here, we have a handful of resources. One of the best ones that I actually love is the right spec sizing tool. I really should have mentioned this right from the get-go. So, right from here, you could size up your system. You click apartments or whatever your actual application is. You plug in some data and it's going to spit out exactly the kind of units that you really require. It's real simple to use. You plug in maybe the number of units that you have. Maybe you're including laundry. You jump right to the end, load summary, continue with product recommendations. And again, like I said, this thing's going to spit out some recommendations. I just kind of put in something real simple and quick. There's a couple different ways to look at it all. You could download it, select it, and it'll give you a nice a bit of information on it, something you can actually look at. Here's the selection report. Oh, you got to actually generate that report. Might be a little bit more than we want to do right now. So, take a look here. You can check out their website. You can navigate to their website from our website. That's rathassociates.com. And so right here, you can get in, you can see all of our training, all of our literature. We're updating the website, so it will have a nice fresh face hopefully soon. And here's the Lars icon. This is exactly how you can jump right to there. So I guess that's my last little closing bit on Lars. Rath Associates, we have everything for your hydronic heating system. In the mechanical room, we also specialize in radiant floor heating. We have controls, we have tubing, we have expansion tanks, boilers, water heaters, separators, air separators, valves, fittings, you name it, we got it. So again, thank you everyone for joining us, and we look forward to seeing you on the next webinar. That's it.
Yep. Thank you, everyone.
Bye-bye.
Bye-bye.